Now, after we complete RAGs, you will get a much better understanding of organization specific use cases. So this is a very, very important topic because especially in organizations and enterprises, RAGs are a absolute gold standard today. Everyone is looking to do RAGs because one of the reasons is because it helps you take into account internal company data, internal company data. So you might have some kind of a document, you might have some kind of you might have some kind of a document, you might have some kind of a PDF file, and you don't want to upload that PDF file anywhere. It's a very confidential PDF file that you want to keep in your company premises, in your server. At the same time, you want to use the Chat GPT model. So it's a very difficult thing, right? Because all this while we are saying that you have to send your data to GPT. Okay, so to use all these LLMs, to use all these large language models, you have to use the API, and there you need to send the data because that's what we are doing in the prompt, right? We are defining a very detailed system message, we are having a very detailed user message, and we have to send the whole data for the LLM to give a response. But what if I want to work with my own company data? What if I have a huge file? What do I do with that? What's the way to work with that? I am not comfortable in sharing that file with ChatGPT because the only option is to send it to ChatGPT, upload it, and send that whole document as part of a prompt. Not that you cannot do it. You can give that whole document as part of a user input. You can do that. You can copy the whole text and you can do that. But then that is confidential data. You cannot afford to do that. So what is the alternative? That is exactly where RAGs come in. So RAGs, this is the broad workflow that we will discuss. We'll see the business use case. We'll take another 2-3 minutes to talk more about RAGs. How are they beneficial? We'll look at the workflow. We'll talk about vector DB and we'll see hands-on implementations. I'll show you one end-to-end demo, and after that we will do one end-to-end case study, which each one of you in the audience will be doing. So that's the plan. And this is just to give you a very pictorial understanding in terms of what we are doing in a RAG system. So we have a document store. This is the internal company proprietary document store that the company is maintaining. And this is where the company's confidential data is present. This is what I was talking about. Okay. So this is where the company's confidential data is present. And you don't want to expose it. This is very confidential, right? This is let's say some bunch of last year sales data or revenue guidance. You have revenue guidance for the last years or employee salary data, which is confidential. You don't want to release it to anybody. Okay, so this is part of your document store. You'll be having it in part of in your file system. At the same time, you still want to build a chatbot on top of it, where people can ask questions and get answers. The same way that we can do in normal GPT models today. You can upload a Word document and you can ask questions and you can get answers to questions. That's the way how this particular process will work out. Okay, so everybody can understand. I hope this is the idea is absolutely clear what we are trying to achieve. Okay, now let us look at the workflow. This is the workflow of a RAG system. Now there's a lot going on. So what I'll do is I'll explain step by step in terms of how a RAG system is designed. So RAGs are a slightly long topic. So we'll do it in two phases. First, today we will see basic RAGs. Fundamental RAGs is what we will discuss in today's session. So we'll talk about building a RAG, using a vector DB, how to create embeddings. This is basic RAG. And some part of tomorrow we will spend on advanced RAG, advanced retrieval. So how do we make it more efficient? How is it done in the real world? Right? Some more advanced topics in RAGs we'll try to also incorporate. Okay. Now, at a very high level, okay, all of you just give it a glance first. Maybe you can all take 30 seconds to just give it a glance what's going on, and then I'll explain. So the first part what we have is, and what I'll do is in this demo, I'll try to take an example of some PDF files only. So let me take that same example and explain this to all of you. Okay. So let's say we have 100-page PDF file, right? So we have a PDF file. Okay, sorry, I think the annotation should be enabled. Just a minute, please. So we have a PDF file, which is 100 pages. And this is, let's say, containing company policy. As an example, this is the company policy PDF file. Okay, so the use case is more like, you can think of a use case where an enterprise wants to build a HR chatbot, some kind of a human resources chatbot where, uh, some kind of a human resources kind of chatbot we want to build where, uh, let's say, you want to know how many leaves are offered in a year. So yes, there is a very detailed company documentation that is also present. You can, of course, go and consult the documentation. But how do we get that answer a lot in an easy way? Okay, so the company wants to create a chatbot, employee HR chatbot, where basic human resources questions could be answered by the chatbot by taking the data from the company policy. Now, company policies are very confidential. You don't want to release it online. You want to, you don't want other people to know, other competitors to know. There might be some very specific compensation packages which are very specific to your enterprise. You don't want to release it. So it's very confidential data. So you want to keep it in-house. You want to keep it in-house in your document store. At the same time, the chatbot should be able to, answer questions based on this. Let's say one fine day you reach out and ask, okay, how many leaves are there in the year? So the chatbot will be able to look up all this information and say, okay, there are 20 leaves in a year, something like that. Okay. Okay. What is the hike policy? Okay. What is the progression policy in the enterprise? Okay. What are the maximum raises given? Or how do I shift to a different domain? Which is again a very common question people have. So let's say you're learning Gen AI. So how do I shift? How do I progress to this? So these are again HR questions. So they might be the model will be able to look up the information and give responses. Okay. That's the idea. So how it works out? Let's see. So we have a PDF file, 100 pages. So first thing that you need to do is you can't, so this is too much to process, right? I know 100 is a very small number, but this could be huge. In fact, some of the exercises we will do in the session, we will actually take very big PDF files. They will be very big. Each of them will be very, very big PDF files we will take. So it might be too much to process all those files in one go. Okay, so processing all the files in one go might be very difficult. So what we will do instead is we will go and break it into chunks. We will break it into pieces. Okay, so and uh, it could be something very simple, like let's say we can say each chunk is one page. Each chunk is one page. So we have chunk one, chunk two, chunk three, all the way up to chunk 100. I want to clarify it doesn't necessarily have to be like this. Now, chunking, there are different strategies of chunking. Chunking can happen in different ways. There are semantic chunkers that can be used to chunk based on the meaning of the context of the document, right? Uh, we can also use the fixed size chunking, like we can chunk based on pages, we can chunk based on certain number of characters. Every 300 characters, I want to create a chunk. Every 500 words, I want to create a chunk. So there can be different ways of doing chunking. But broadly speaking, we take the entire 100-page PDF file and we try to divide that PDF file into 100 chunks. Simple. Every chunk is one page. Simple. Now it's more manageable. Now what we do, because see, this is all text data, right? Even when you chunk it, even those 100 chunks that you see, this is all text, right? This is everything is text data. Each of those 100 chunks are basically text. Chunk one is the whole text present in page one. Chunk two is the whole text present in page two. Chunk three is the whole text present in page three. Chunk four is the whole text present in page four, right? So okay, just 1 minute, please. So every chunk is ultimately text. Now what you need to do, the next step, what you need to do is you need to go and save these chunks in the vector DB in an embedding form. Remember, I told you that machines cannot understand numbers, right? Sorry, machines cannot understand strings. Okay, so convert text to numbers, text to numeric embeddings. So how do we convert the text to numeric embeddings? This is done using a vector DB. This is the same idea that was playing out during the BERT score. If you remember, I told you very briefly that how you take the sentences or the generated text and how the machine is converting that into the context, into the embeddings, right? So the idea is very similar because machines cannot understand text. Machines cannot understand strings. So you take each and every one of those chunks, which are nothing but text, chunk 1, chunk 2, all the way up to chunk 100, and you somehow represent them as a vector of numbers or features as we call it. I'll give some random numbers f1, f2. So we are representing every chunk as a vector of two numbers. Let's say chunk 1 is 0.1, 0.2. Chunk 2 is 0.11, 0.22. And chunk 100 is 0.9, 0.8. Okay, so I'm just saying that the embedding size, okay, just a minute. I'm just saying the embedding size is equal to 2. What does it mean? It means that I'm converting every chunk into a vector of two numbers. I'm vectorizing the text. I'm basically representing the chunks or basically text here as a vector of two numbers. Now, why two? No particular reason. It's just an example that I'm showing you to explain the concept. But you can decide how many and what kind of an embedding model that you want to use. And there are separate embedding models that will do this for you, right? So this is not a manual process. So after that, so chunking will be done by chunkers. There are a lot of these chunkers that are available that you can use, which we'll see in the demo. And even the embedding, the part where we are doing the embedding, even this embedding will be done using, just 1 minute, what happened here? We got removed by mistake. Okay, yeah. So even the embeddings will be done using embedding models. And different embedding models will embed in different ways. Some embedding models are very advanced. They might take each and every chunk and create 1,000 dimensions, or they will take the text and convert into 1,000 numbers. And remember, the more the embedding size, the richer the context. The more powerful models will take the text and generate more numbers out of it. It is trying to represent the text in terms of numbers. And the more the number of numbers, the richer the representation. You're able to represent the text in a richer manner. That's the context. Anyways, the vector DB creation is done. The vector DB works like any other relational database or NoSQL database. Think of it that way. The ideas are very similar to a NoSQL DB. So you just store unstructured data. And it's not only with respect to text, it's also with respect to pictures. Although we are not discussing images right now, but the idea is very similar for images also. In case you have a question, how do we save pictures? The idea is very similar. Just like here, we take the chunks and we store the chunks and we represent the chunks as numbers. The same applies for pictures. We store the, excuse me, we store the images. So image 1, image 2, image 3, and then we represent those images as numbers, as a vector of numbers. The idea remains very similar, even with respect to pictures. Now, once this is done, once we have created the vector DB, now we know we have the chunks and we also have the representations for the chunks. Now come to the second part. This is usually the first part of the whole RAG workflow, the vector DB creation. Even when we see the demo, we will see the exact way. The first part that we will do is the vector DB creation. We take the document, and from the document, we do the chunking and we create the vector DB. And this process usually takes time. This process is usually very compute intensive. And sometimes GPUs are needed. We will need to use graphical processing units, GPUs, TPUs, advanced hardware. More compute is needed to perform this part. Okay, just keep this at the back of your mind because this is a one-time process. This is not something that you have to do every time. So right at the start of your project, the vector DB creation is a one-time process. You take the entire company's data and you create the vector DB once. And then obviously incrementally as changes happen, you can update just like how you do in a database. If you have some new records that are coming or some new pages are getting added, you can update in the vector DB. But the initial creation part will take time. Now, now let's talk about the retrieval. How does a retrieval happen? Let's talk about that. I will use a different color just to highlight it. So here you ask the question. Now here you ask the question, who is, how many leaves we get in a year? How many leaves we get in a year? Remember, that's the user query. This is the user input. So this will be some kind of an application that you will build, right? So the users will have no idea about all this RAG and all that, right? So you're an employee in the company, and you will use some kind of a application, or you might have a mobile device where you can access it. You will have some kind of a user interface where you will go and type this question, and that's your user input. That's your user message query. Remember, machines cannot process text. Machines don't understand strings. So again, that query has to be converted to numbers. So machines cannot process text. Machines don't understand text. So what has to happen? That query has to be converted to a numeric vectorized form. So this entire query has to be converted to a numeric vectorized form. So whatever query we have right now, let's say the corresponding embedding for that query will be 0.12 and 0.23. I'm just giving a ballpark number, okay? Let's say this is the corresponding vector embedding for that query, 0.12 and 0.23. So whatever query the user is asking, the user message will also need to be converted back to its corresponding embedding. And now we will have to check, the retriever module will go and check in the vector DB that this question is similar to which of the chunks. So whatever question we are asking here, this question is similar to which of the chunks? Which of the chunks that this question correspond to? And that is how the retrieval will happen. So based on the question that the user is asking, based on the I think this is understandable. So I think the orientation changed a little. So that's okay. It's not a showstopper. People can all make it out what was written. So anyways, so just to clarify, we took the documents, we chunked it, we created the chunks, and then we saved it in the vector DB. And in the vector DB, as I was mentioning, the chunks are all saved in an embedding format, right? So every chunk is converted to a vector of numbers, and those embeddings are what are saved in the vector DB. Now, when the user is asking a question, so here the question that is asked by the user is, hey, how many leaves do we get in a year? This is what is written here. How many leaves do we get in a year? Now this text, machines cannot understand the text, right? So this text has to be also converted to its embedding. So we have to convert this text into its respective embedding. We will convert this text to its respective embedding, and let's say the embedding looks somewhat like this: 0.11, 0.23. So this is the corresponding embedding that we are getting, 0.11, 0.23. And now the retriever will go and go back to the vector DB. The retriever will go to the vector DB and check that whatever user question is asked, that user question is similar to which of the chunks in the vector DB. So whatever user question is asked, this user question is similar to which of the chunks in the vector DB. That's the way to look at it. So whatever user question we are asking, which of the chunks is it the most similar to? So this user question is most similar to, let's say, the first two chunks. This is the distance formula that we are checking. I think you can relate to it. Like you can see 1.12, 0.23. This set of numbers is very similar to 0.1, 0.2, right? So this set of numbers is very similar to 0.11, 0.22. So it's basically looking at those 100 chunks. We are looking at the 100 chunks and retrieve the top two chunks based on similarity. Now again, it doesn't have to be exactly this way. Doesn't have to be exactly the top two chunks. And again, we can decide that it's a hyperparameter. We can decide how many chunks we want to retrieve. So here is an example. So given any user query, I want the retriever to retrieve the top two chunks. Whichever chunks are the most similar, the top two chunks I want to retrieve. I want to retrieve. So here, chunk 1 and chunk 2 will be retrieved. You can see C1 and C2 will be retrieved. And this will be now part of my context. Okay, this will be part of my context. So until here, I hope it's clear. So until here, everything was happening on premises. Nothing leaves my server, nothing leaves my enterprise. Everything is happening in my local computing infrastructure. The documents are maintained locally. The vector DB is hosted in my local server. Although there are cloud vector DBs you also have, but if it's very sensitive data, you can host it locally. Okay, so vector DBs are all hosted locally in my local infrastructure. Okay, even the retrieval will happen locally. So based on the user query, you will retrieve the top chunks. Even that retrieval will happen locally. And now you have those chunks with you. This is the last part where you're invoking the GPT model. So in the LLM, what you're sending is just these chunks. You don't have to send the whole data. You are only sending the chunks. Okay, so what will happen at the final step? So based on this question, the model has retrieved the top two similar chunks, which potentially answer the question. But then these chunks are in a very haphazard manner, right? I told you the chunks are basically nothing but page numbers. So because the chunks are page numbers is kind of very haphazard right now. So now what you want to do, you want to go and effectively use a large language model to streamline the response. So now the chunks are nothing but disorganized pieces of text that are retrieved. So now you will go and send this data to the large language model, and the large language model will give you the refined summarized response. And what are the important parts? What are the inputs to the large language model? As we do the demo, we will see this shortly. So one is the system message, obviously. Okay, system message plus prompt parameters. This is your temperature, the max tokens, all that. Plus user message. User message will come from here, mind you. This is the original user query. So the user message will come from here. I'll write down user message plus the retrieved context. The context will come from here. The context is what is retrieved. So, okay, plus user message plus context. Actually, this whole thing is part of the user message. When I say user message, this whole thing is part of the user message actually. Okay, so this is basically what will go to the LLM as part of the API call. Okay, so you're feeding what is the question the user is asking. You are also feeding to the LLM what is the retrieved context. What is the context we're retrieving? Because the LLM will not answer the question based on its own internal memory. Remember, you can, if you go to chat GPT and if you ask the question that how many leaves do I have in a year, GPT model will not be able to answer because GPT model does not have information about your company policy. It will try to take an approximate guess, but it will not be able to give you the correct answer because it doesn't have that information about your company policy particularly. So you will have to give the original user query and you will also have to give the retrieved context. Both will be part of the user message combined with the system message prompt parameters, and that whole thing becomes a prompt. And that is what is be part of the API call, and you get a response. This is a retrieval augmented generation. And if you see, why do we call it a retrieval augmented generation? Because obviously it's a generation problem, very similar to the meeting summarizer, all that we were discussing, but it's an augmented generation. And the augmentation is happening based on retrieval. So first we are retrieving, and then we are augmenting. So first we are retrieving the chunks, and then we are generating the augmented response. It's not a normal GPT response. Normal GPT response would be just where you write a straightforward prompt and get the answer. But this is the augmented response. So as part of the user message, you're giving the input and the retrieve context. And the answer the GPT model is giving is not a normal generation, but it's an augmented generation based on the retrieve context. Okay, so that's what a RAG application basically is.